This smooth, undulating surface represents how physical properties like heat, fluid dynamics, and electromagnetics actually exist in the real world. They form a continuous, infinite spectrum of values across space. But computer hardware cannot process infinity. A computer possesses finite random access memory. It cannot store the infinite decimal places or the infinite geometric points required to calculate continuous calculus. To simulate reality, we have to slice it. We sample the continuous field and lock it into a finite grid of discrete floating points. Once we lock these discrete points into a grid, we can apply localized math to predict complex behaviors, like how heat diffuses across a solid block of metal over time. The primary task of computational physics is taking the continuous, infinite laws of calculus and converting them into localized, discrete algebraic steps that a machine can actually execute. Look at this two-dimensional coordinate plane. We have a dashed curve representing a true physical function, but our computer only knows the exact values at 3 disconnected data points, f1, f2, and f3. How do we calculate a derivative, the slope of the curve, when the continuous line is missing? The simplest estimate uses basic algebra. We calculate the slope by finding the rise over run between 2 adjacent points. If we calculate that slope using data strictly ahead of our target point, we get a forward difference. If we use the data behind it, we get a backward difference. Both provide a rough estimate of the true slope. But evaluating the derivative at a midpoint by spanning symmetrically across the data from f1 to f3 gives us the central finite difference. Notice how this line perfectly parallels the true tangent slope at f2. We always prefer this tight, centralized geometric spacing because it strictly minimizes the calculation error compared to the asymmetrical forward or backward methods. A finite difference is ultimately just a linear sum of scattered function values. Its mathematical accuracy depends entirely on how perfectly centralized the calculation is relative to the surrounding data points. Watch how that 1D logic scales. The single line rotates and expands into a top-down, two-dimensional grid of nodes, mirroring the reality of a physical surface. We define any central target node with an ij coordinate. To calculate the physics at this specific location, the finite difference equation reaches out to the adjacent cells, up, down, left, and right, gathering geometric data to form a 5-point cross-shaped stencil. This structure maintains the exact same rise-over-run logic we proved in one dimension. It just applies the math simultaneously across the x and y axes. Any two-dimensional physical space, no matter how complex the geometry, can be computationally mapped as an interconnected web of these localized central finite difference stencils. We face a hardware paradox. Physical interactions happen in 2- and 3-dimensional space, but computer RAM chips store memory in a strictly flat, one-dimensional linear sequence. Here is how we thread a string through the 2D grid, row by row. When we pull the ends tight, the entire spatial plane is rastered. It collapses into a single vertical 1D column vector of unknown values that the computer memory can actually store. To solve for those unknown values, we introduce the system matrix. This is a massive grid of known coefficients that pre-multiplies our new column vector. The architecture of this matrix is highly specific. Each horizontal row represents the exact governing equation for one single physical node in our original grid. The vertical columns dictate the relative coupling. They map exactly how that specific node mathematically interacts with its spatial neighbors. Building a computational matrix is the act of physically translating 2D spatial topology into a 1D language that hardware can process. This partial differential equation describes 2D transient heat conduction. To calculate numerically with the FTCS method, we swap continuous spatial and time derivatives for discrete finite differences. Basic algebra then isolates the future temperature of a node on one side, moving all current terms right. Because FTCS is an explicit method, the exact future state of any point can be calculated directly using only known data from the present moment. This copper plate is discretized into a 4x4 grid. Outer nodes are physically locked at 100 degrees, while the interior nodes start at 200. As time steps forward, the explicit loop triggers. Interior nodes read cooler neighbors and update their temperatures, actively diffusing heat outward. But this explicit loop operates under a strict mathematical limit controlled by the diffusion number. This parameter groups the material's thermal diffusivity, the time-step duration, and the grid spacing into a single stability metric. For a uniform 2D grid, if the diffusion number exceeds 0.25, the simulation breaks. The discrete errors inside the equations amplify infinitely, and the nodes violently oscillate into impossible mathematical values. If you apply an unstable diffusion number to a physical system, the material violently distorts and shatters into digital static. A successful simulation bridges abstract calculus and physical reality. But that bridge holds only if we strictly balance the resolution of our space against the pacing of our time.